I have three co-authors, Simon Hudiger, Pierre Taras, and Elliot Wagner. Simon is in the audience. Let's see, here is my thing. I'd like to start out with this picture to let you know that this is a philosophy talk. Oh, back in the cage, okay. This is an ancient debate that I'm addressing. Locus classicus is the Platonic dialogue, the Cratylus. There was an ancient argument about how names, or in general signals, if we would think about it, arise. Democritus, who was probably one of the first true scientific philosophers, thought that there was some kind of dynamical process that had some chance element in it. And language arose in the way that this dynamics worked on the chance fluctuations that you had. And the other side thought that there was something innate that led you to language, right? And you know, this debate went on forever, right, in philosophy. So we could think about these questions in terms of signaling. Signaling is a large area, if you want to think of it globally. Some entities have information. They send signals to others. The signals may or may not convey information. The receivers react, and there are some payoff consequences. Payoff consequences drive some kind of dynamics, right? Because if you're going to think about Democritus, there has to be some dynamics. And something happens. Democritus said, the word is the shadow of the deed. Right? So that's the theme of a certain way of looking at the genesis or spontaneous emergence of information transfer by signals at a high level of abstraction. Well, payoffs could be all sorts of kinds, right? We could have common interests, opposed interests, mixed interests. The payoffs might be a function just of how the receiver reacts, or they might be a function of the signal sent as well, as in costly signaling theory. Signaling may involve many senders and many receivers in some sort of network with various kinds of network structure. This talk, I'm going to focus on the very simplest games. Most of it has one sender and one receiver. Some of them, at the end, there will be two senders who send each other signals and then react and then do something. Cheap talk, pre-play signaling in games. Okay. The rest is all part of the philosophical problem, but we can't say very much about it. There are all sorts of adaptive dynamics that we could discuss at various levels, evolutionary levels, learning levels, social learning levels. So we're going to focus on three different dynamics: replicator dynamics, and variations for large populations, evolutionary dynamics, frequency-dependent Moran process for small populations, and reinforcement learning for individual learning. Of course, as we've seen in previous talks, the first two kinds of dynamics have learning interpretations too. So they can be thought of as being driven by differential imitation rather than differential reproduction. So what I'm going to do today is not attempt any sort of general survey, but rather give you some examples, some snapshots where we look at these dynamics and where dynamics add something interesting to the equilibrium analysis of the signaling game. So we start with infinite populations, replicator dynamics. Okay, we know what that is. We got a talk on it. The first kind of game I'll discuss are common interest games. They were introduced by David Lewis, a philosopher actually, who did something interesting in his book on convention, right? He invented sender-receiver signaling games with pure common interest as a model of how meaning could be conventional, right? Since there are separating equilibrium that are multiple and each is as good for everybody who's in that equilibrium as another one, right? Then the meaning of signals is purely conventional because it's a function of which equilibrium society has settled into. So in the simplest sender-receiver games, the sender observes a state. Nature flips, well, okay. We'll look at the simplest one first, right? Nature flips a fair coin to choose a state out of two states. The sender observes the state and chooses one of two signals. The receiver observes the signal and guesses the state. Okay? Correct guess pays off one for both, otherwise nothing. It's a partnership game. Okay? The equilibria in this game consist first of two signaling systems, one in which A means state 1 and one in which A means state 2. A whole plane of pooling equilibria where the sender's probabilities are independent of the state and the receiver's probabilities are independent of the signal. If we look at two population replicator dynamics, signaling systems are attractors. Each of the pooling equilibria is dynamically unstable. Anything that moves off the pooling equilibria into the interior of the simplex gets carried to one or the other of the signaling system equilibria. Okay? So meaning emerges spontaneously in this case from almost every starting point, which gives a positive answer to Democritus' question in this Lewis signaling game. Well, that's a nice example, but is it true for more complicated games, or is this a very special case that we've looked at? Well, we should be suspicious because the model isn't structurally stable. It has this connected component of pooling equilibria. So any small perturbation of the model may lead to radically different conclusions. We'd like to look at some plausible perturbations of the model. And the first one to think about is, well, maybe nature doesn't flip a fair coin. Why should the two states be exactly equiprobable? And then the result isn't true anymore. Of course, the signaling systems are still attractors. The component of pooling equilibria collapses from a square to a line where the receiver always does the act that's better in the most probable state. Right? And the sender sends no information. The interior points of this line are now stable, not unstable, although endpoints are unstable. The line itself can't be an attractor in the technical sense, right, in line with a theorem that we heard yesterday. But nevertheless, it has a basin of attraction. That is, there is part of the simplex, or polytope here, we're doing two populations. There is a part of it that has positive volume that all gets carried to one of these pooling equilibria. Well, so in this picture, signaling can arise spontaneously, but it's certainly not guaranteed. But this itself is a model which isn't structurally stable because we have a whole line of pooling equilibria. So we should be a little suspicious of that too. So we'll perturb that by adding a little bit of mutation. Okay? A little bit of mutation now puts pressure on this line that drives it away from the endpoints towards the center, and the line collapses to a single point. Okay? And this is an infinite population model, so we still have deterministic dynamics. The question then is, here's a single point. Is it going to be dynamically unstable, in which case we've recaptured the idea that with probability 1, we have generation of a signaling system, or is it going to be dynamically stable, or an attractor, in which case we've lost that strong conclusion? Well, we can't say yes or no because it depends on certain things. It depends on how great the disparity in the probabilities of the states is. And this is a two-population model, so it depends on the relative mutation rates of the two populations. Okay? This is all analyzed in an article by Josef Hofbauer and Simon in Journal of Theoretical Biology in 2008. Just to give you a feeling, suppose that the mutation rates are equal in both populations. Then, if the disparity in probabilities isn't too great, this pooling point is dynamically unstable, and you converge to a signaling system with probability 1, just as in the original model. But if they're too unequal, there's a bifurcation, and this turns into an attractor, and you lose this. The bifurcation point is about there, about 0.78, right? So there's a large region in which you have convergence to a signaling system with probability 1. Oh, I should say, as a footnote, disparity of probabilities could be replaced by tinkering with the payoffs, right, and getting the same results. But suppose the mutation rates aren't the same, and the receiver mutates or experiments, if we think of this as a learning model, at least twice as much as the sender. If that's the case, this single point is always unstable, right? No matter what the disparity is in the two, and the probability of the two states of nature. And then you get the strong result that you always converge to a signaling system. Okay, that's just a little snapshot of something with pure common interest. It surprised us when we found out that things were so much different when you moved off of the first model. Suppose we have opposed interests, zero-sum games. Only Nash equilibrium of the one-shot stage game is no information transfer. Replicator dynamics may never reach equilibrium, as we've seen illustrated a number of times. We're going to revisit them. So if we have this kind of payoff matrix, and we look at the part of the space where both sender and receiver use separating strategies, Then we get a matching pennies kind of setup where you have cycles around the mixed equilibrium at a half, right? But this is not structurally stable, so again, we should worry about this. And of course, you can perturb it a little bit so that the cycles will cycle in, or you can perturb it a little bit in the other way so that things cycle out. But here's something that is structurally stable. This payoff matrix is a version of rock, paper, scissors. It doesn't look crazy or in any way, but the dynamics that are generated are chaotic, right? Here's a picture of just one part of the polytope where one of the populations is cycling between separating strategies. Right? And you get chaos. This is shown by Elliot Wagner. The kind of chaos that you get is actually the kind that was first shown by Sato, Akiyama, and Farmer in 2002 in a paper in PNAS, right? So you have two population Hamiltonian chaos. It's structurally stable. Right? So this is something that's, that we can think of as real, if that's our test. If we move to mixed interests, we should note that cycles which cycle around an equilibrium can occur in a non-trivial way in games that aren't simply made up to do these cycles, but in games that have serious applications. For instance, first, the Spence signaling game. Spence himself noticed that you could get cycles in the Spence signaling game for certain parameter values. Noldeke and Samuelson formalized the Spencean dynamics and demonstrated cycles. Elliot Wagner applied replicator dynamics and best response dynamics. One of the interesting things is not only that you can get cycles, but that the cycles are on a face, right, where the populations circle around what's called a hybrid equilibrium, a kind of mixed equilibrium, but that face attracts things from the interior, right? So it's not just a phenomenon of being on that face, but it's something that, in fact, for the best response dynamics, since things go in a straight line, it's possible to calculate for an exam, for given parameter values, the exact size of the basin of attraction of the chaotic regime. Right? And it can be quite substantial. Hudiger and Zollman found a similar sort of phenomenon in the Sir Philip Sidney game, costly signaling, two costly signaling games. Here's a picture of orbits being sucked out to this face and then cycling around a hybrid equilibrium. Okay, so those are my snapshots of replicator dynamics in three different regimes of signaling. And now I'm going to say something about finite population dynamics, frequency-dependent Moran process with rare mutations. Okay. Here's how it goes. Everyone plays the base game with everyone else, so this is a round robin to establish fitness. It's a little bit of a cheat, right? But it's there's supposed to be a long time between mutations, so this is the way it's set up. One individual leaves the group or dies. a new individual walks in the door or is born. New individual in the social learning implementation of this imitates a strategy in the population with probability proportional to its average success. Okay? So that's the frequency-dependent Moran process, which is the underlying stochastic dynamics, and then we add some mutations. Oh, well, no, I haven't added them yet. Okay. So if we're in the frequency-dependent Moran process, it's a Markov chain. Every monomorphism is an absorbing state. Right? That's not very interesting. So we add mutation. This new member with some probability chooses any strategy. And that includes strategies which are extinct. So it's a difference between mutation and imitation, right? You can only imitate strategies that are in the population, right? Strategies that are extinct can't be imitated, but they can enter the population by mutation. Okay? And Markov chain is now ergodic. And we would like to study the small mutation limit, that is the proportion of time that a population spends in states in the limit as the mutation rate goes to 0. And Fudenberg and Imhoff in 2006 show that to calculate this, it suffices to study the transition probabilities between the monomorphisms, which are initiated by one mutation. So in a monomorphism of the group, one mutant walks in. Either that mutation takes over the whole population or goes extinct, right? And then you're back in a monomorphism, right? We study these transition probabilities. There's then a Markov chain between those transitions where the new states now are monomorphisms. And we get our limiting result. Okay. I want to apply this to a game of this type. Sender is one of two types, which we can call high or low. The sender sends one of two cost-free signals. The receiver has two acts, one which she would prefer to use with the high-type sender, and the other for the low-type sender. But the sender would always prefer to be treated as the high type. Okay? So you can see in this sort of setup, the only Nash equilibria of the game are pooling equilibria. Here's a specific numerical example that I'll use to show some results. And you can see that this is a game of the kind that I described. And we'll fill in details by saying that the probability of state 1 is 0.4 and state 2 is 0.6. To apply the Fudenberg-Imhoff technology, we need to symmetrize the game and look at it as a one-population game. So now we look at a game where you have roles of being sender and receiver in this game, 50% chance of being each, and we'll look at a small population size at 50. Here's the long-run behavior. The population spends most of its time successfully signaling, right, in the separating equilibria, and much less of its time in the Nash equilibria of the one-shot game. If the population size gets bigger, this effect gets smaller and smaller, and in the limit, this model converges to replicator dynamics, right? And you wouldn't see anything like this at all, right? But in this specific small population rare mutation case, you in fact see viability of signaling where analysis of the one-shot game would suggest that it isn't possible. There's related work in pre-play exchange of signals, both in the stag hunt and in the prisoner's dilemma. So the setup here is each of two players, sends the other one a signal, right? And then they play the base game. The base game could be either the stag hunt or the prisoner's dilemma. Small population, rare mutation limit. The amount of time that's spent cooperating in the stag hunt gets much larger than it would be in a large population. And you spend some time cooperating in the prisoner's dilemma, although you wouldn't in the large population. Okay. And that's true even if each player only has two signals. But if the players have lots of signals, then these effects are amplified, okay? Which may not surprise people in light of Art Robson, Darwin Nash, and the secret handshake. That in the prisoner's dilemma, secret handshakes can come in, and it takes a while for them to be displaced, and new ones can come in. So, of course, more signals are better. Okay, third section is learning. I want to talk about reinforcement learning in the sense of Herrnstein and Roth-Erev in their most plain vanilla model. Right? So there, in the 1995 paper, there's some tune-up with recency effects and some other things. But the plain vanilla model just uses Herrnstein's matching law, that at each point the probability of a specific choice is proportional to the accumulated rewards from that choice in the past. Okay? And there's some, learners are started off with some virtual rewards sitting in their urns, so to speak. And then the dynamics proceeds like this. The mathematics for analyzing this is a little different. It's stochastic approximation because as the reinforcements pile up, the jumps become smaller and smaller, and the stochastic process approximates the mean field dynamics more and more closely. And there are results about limiting behavior that allow you to get rigorous results about limiting in this kind of learning in specific games. And of course, there are lots of other kinds of reinforcement, and there are various ways that this could be modified. But if we're thinking about limiting behavior, they all change everything, right? They're all different. Also, I should say, if you're thinking about individual learning and you're thinking about signaling games of the kind that I'm talking about, and you wanted to design a learning dynamics that would do really well, it wouldn't be a problem at all. Right? What's more interesting for us is to try to take a dynamics that at least has some empirical support and investigate how well it does. So let's return to the simplest Lewis signaling game with which I started. Two states, two signals, two acts, pure common interest. The states are equiprobable, and we use this kind of reinforcement learning. So let's assume that, because we're philosophers and we're interested in Democritus, we're not going to reinforce strategies, right? Because that would require the players to be thinking in terms of strategies. We're going to reinforce acts, right? So the players don't need to think about strategies, and they don't even need to know that they're in a game. They just have to tote up, do something, and keep track of the reinforcements that they get when they do it. So the sender gets a stimulus, right? That's the state. Sender observes the state. And has a reinforcement earned for each state. For sake of definiteness, we'll suppose that each urn has one A ball and one B ball in it. But it doesn't matter as long as the number of balls is positive. Okay? And you can have fractional balls. And the receiver has one urn for each signal. Initially, it's got some positive number of balls for guessing state 1, or guessing state 1 makes it look like he's thinking about state 1, but actually doing the act that pays both of them off in state 1 is a better way to put it. Right? The receiver has an urn for each signal. So that defines the stochastic process. I don't have to tell you this because that's about how it's done. But the result is that in this setup, you again have convergence to a signaling system with probability 1. You might think that because this kind of reinforcement learning has strong connections with replicator dynamics, that this would be really the first part of the talk all over again. But it's not quite so easy. Right? It took some work by, mostly by my co-authors, to actually get a rigorous proof that this is true. What if we have not 2 states, 2 signals, and 2 acts, but n states, m signals, and n acts? So we've got an act that matches each state, right? But there can be excess number of signals, or there can be not enough signals to get full information transfer about the states. To state the result, the main result of this paper, I have to talk about a bipartite graph between states and signals. And you might think that you'd have to also keep track of the graph between signals and acts. But the symmetry of this game allows a certain reduction, as it did in the previous result. That is, the sender gets paid off a 1 exactly when the receiver gets paid off a 1. So the information that drives the dynamics is really all contained in the sender's urns. We're going to consider a graph that maps a state. I call it a situation here because we got states of the Markov chains earlier, to a signal if in the limit of this process there's a positive limiting probability that that signal is sent in that state. Okay? And it will turn out that there also then will be a positive limiting relative frequency that the act corresponding to that state is done on receipt of that signal. Okay, so the main result is if this kind of bipartite graph has the following property, about to be stated on the next slide, then reinforcement learning converges to it with positive probability. Each connected component of the graph has just 1 state or just 1 signal. Okay? And each vertex has an edge. Okay? And we're saying this is sufficient for positive probability of ending up that way. We're not saying it's necessary because that isn't yet proved, though it may well be true. So here's an example of a signaling system where each situation is mapped to a unique signal. And here's an example that exhibits synonyms and bottlenecks. That is, the third situation from the left is mapped onto two different signals with positive probability. They're synonyms, right? Whereas the final two situations are squeezed onto one signal, right, which is an information bottleneck. Okay? So we can't have pure information transfer, but this still has the property that was stated. So with positive probability, you have this. That's a little different from the nicer result that we got where we had two states, two signals, and two acts, right? And a little caution that you can't generalize hastily from those. One question when you have an excess number of signals is whether synonyms persist in the population or whether one signal may drop out of use. Right? I don't know. Do you have any intuitions about what will happen? It's not clear. You might think, well, one signal will be used a little less, right? And then it'll get reinforced less, and then it'll be used even less, and so on. It'll drop out of use, and you'll end up with two states, two signals, two acts, right? But that's wrong. So you can show that synonyms persist in this case, right? Always persist. So my punchline is, maybe I should put it as a personal confession rather than waving a flag, right? Starting and looking at these things for philosophical reasons, I looked at the simplest cases, and it looked like the answer was pretty clear, right? But when you look at the dynamics, things become much more complicated and nuanced. Thank you.